So, what have we got going here? All right. So I'm going to show how you make an exploding pixel effect with 0 frames of animation, so like from a still image, while at the same time being able to do so with 0 memory footprint. So we're going to create just a little object here to explode. All right. And then quickly make our draw function, our get function. Oops, I need underscores. Clear the screen, draw the sprite, and then there we go. Okay. So this particular method, this particular effect relies on a property of random numbers that you can use for, I think, for any particle system that you want. So you set the seed random number before you begin, and that's it will give you a set of random numbers every time you call rand. And if you call for the same number every single time, you'll get the same random number. So what we want to do is we want to, for each pixel in this sprite, okay, that's not a background color, let's say. So it's not black. It's not 0. We want to take that pixel, choose a random direction, okay, and animate that pixel moving in that random direction. So we should really just start with a single color, single pixel. So pset, so we'll pset 7 white at like some random location, okay? So we'll do that. And we'll do that in here, in our draw. Right there. So that's that yellow one. Okay. So now let's give, it's not very, useful. So let's create a structure to hold this all in as our particle. Okay, so we're going to do this as a traditional particle system first, and then we're going to optimize that particle system by removing the additionally needed memory. So at first, we're going to take where our pset at 4242, and we're going to put that into P. Okay. So we're going to do p.x and then p.y. All right. Same spot. Renders the same image. Okay. So now what we're going to do is we're going to update and move in a random direction. Now, typically, I like to create a vector table for this to use so that I can do it more succinctly as add, subtract, normalize, magnitude, multiply, and those types of operations on vectors, because it's easier to do the vectorization of from the starting location to the pixel location. Okay, but we're going to do this differently. Okay, so we're going to set up another position, which we're going to call our start position. Start X, start Y. And we're going to set it at 3232. For now, we're going to take our image and just get rid of our image. Okay. So now what we want to do is we want to choose from the starting location. And I kind of misspoke earlier. So what we're going to do is we're going to do this explosion as that pixel is going to fly off from the center of the image in the outward direction from the center at a random speed. Okay, so we're going to choose a random speed for it to go in that direction. So we can always recalculate the direction that it's going to go in and update it appropriately. Okay, so we have this as our starting position. So we'll make our starting position, this is not supposed to be that. This is supposed to be maybe that. Oh, here we go. Start X, start Y. Okay, so we got 2 points. One's our start, one's the yellow is a start, white is the particle position. Okay, so now if we want to update these, we need a directional normalized vector. Okay, so let's figure out what direction we need to go in. So it's going to be the pixel position, okay, minus start position. Okay, and I might get this wrong. I get these flipped around all the time. Okay, we want to normalize this. Okay, so we need to find the magnitude of this vector. And we need to find the magnitude first. Okay, first you need to calculate the magnitude, and then you need to divide each of the components by that magnitude. In order to find the magnitude, you need to double each component, or multiply it by itself, not double, but multiply each component by themselves and add that together, and the square root of that will be your magnitude. So if we did an m here, it would be the square root of dx times dx plus dy times dy. So it's each component multiplied by itself, and then added together. The sum of that is square root, the square root of the sum. Okay, so that's the magnitude. And then what we're going to do is we're going to divide each component by the magnitude. Now, what this results in components that are always between 0 and 1. Okay. So that no matter what numbers you have, you will always get a number between 0 and 1. Okay. So now that is in 0 and 1, it's still in the same direction that we want it to be in. So if we were to draw a line from 0, 0 to wherever this dx dy is, and then move it to our starting location, that would be pointing in the direction of the particle. Okay, so now that we have the normalized directional components, we can use those to multiply by any kind of speed we want. Excuse me. And find a new position for P given a time T. So what we'll do here is we'll create another variable T to be updated, T plus equals 1. Okay, so that's going to be our time T. And we're going to change the value of P. We need an initial value of P, X and Py, so we'll say Ix equals the same and Iy equals the same. So we'll save off an initial value of X and Y for P and use that. So we'll use the initial value times time times dx times a random number, which we're always going to be guaranteed the same random number. So this will in essence be our speed. We'll do a maximum. So we'll say 8. And then we'll do the same for the y component here. dy times rand 8. Okay. So that's based on an increment of time. We're going to take the direction and multiply it further and further along this path. So this directional vector is a certain direction in the y direction, a certain amount in the y direction, a certain amount in the x direction. We multiply by the time taken, okay? And this will change our pixel position. So you're going to see it move off in a random direction. Did I do that? No, we're going to see it move off in a direction away from yellow, or toward it. I think, I don't know if I got this minus right or not, but yep, we did. Okay, and it will always move off, no matter how many times we run it, it will always move off in the same direction, but I think the coordinates are flipped, and then it came right back because the integers overflowed. Okay. Oh, I know why. This speed here is different for each direction. We want it to be a single speed for both directions. Okay. So now it should, yes, correctly move off in that direction away from the starting location, and not a random random direction from there. We can add jitter to this if we add some more random numbers to try to give it that little a little turn from where it is. We could add successive random numbers to it to kind of give it like a jitter every couple of ticks or so. But essentially, we are still updating a particle, right? Okay. And all we needed was the initial position. We are drawing these each time. So why don't we, because this is all based on t, and it has no, it saves no state, we can actually take this whole thing and create a function ppos, okay, for particle position given time t, okay, and we need to know a few things. So we need to know the starting x and the starting y. We need to know the p initial x and the p initial y. That's it. Okay. So if we know this, and let's take the let's take the speed. Okay. We're going to need to take the speed as a parameter because we want to be able to run this and not care how often we run it. Okay, so if we not use the particle at all, okay, so we're going to do this refactor, and we're going to, so this is using, oh, the current position to check. Okay, no, we can use the initial position as the directional vector because the particle is going to be moving along that same trajectory, so it's going to be somewhere in that line always. Okay. Now, this gives us a new pxpy, right? So let's try it. Oops. P.x, comma P.y equals P pos, pass in T, and then we'll pass in our SX, SY, and then our P.ix, P.iy. Okay. Oh, I made a mistake. Local SP. Okay, yeah. We did not pass in SP. Okay, SP. There you go. And it's the same direction. It's moving in the same direction at the same speed. Okay. So now we don't even need the P structure whatsoever. Right. So in essence, we could do this calculation. We don't have to do this calculation here. So we can actually get rid of P and do this calculation right here. And we don't need to set it to px. Okay. And we know what our initial position was. 42. Right? 42s. They don't change. That initial position does not change. Neither does the SX and SY. This was 32. 32. Okay. Okay, so we can get this. Oops. Okay. And then all we need really is the SP. Okay. So we'll do the SP rand 8. Okay. And as long as we set the seed, right, it'll be the same every single time. There it goes. Look at that. Exact same. So now we're not really storing state, we're not really updating anything. We're just using this function every single time. And a random number for the speed for the particle. If we set the random, right, we set the random seed, this speed for each particle that we call will be the same each time. So now what we want to do is we want to go from 1 to 8, right? For y, 1 to 8, okay? And we're going to say locals. We're going to do this for a particular sprite. So we're going to say for sprite 1, we want to get color for the sprite 1. So here, we use the sget. Okay. Use sget xy. This gets the color. If color is not 0 or background color, or background, BKG for short, then we're going to draw it p set, and we're going to get the time t, right? And the direction. So we need the speed, right? Which will be our random speed. This will be the same each time because we're resetting it here. Reset sequence. So at I'm going to say sx plus x, sy plus y for color C. Okay, so we're going to draw the color, all right? Now we're going to get our. What we're going to do is we're going to calculate an offset, right? The particle effect here, or the position. It'll just be the position actually. So we'll have px, py, and these will be. So this is the sprite x, sprite y, and then this is x, y. Now we're going to calculate it from the center of the sprite. So we're going to offset the beginning by -4 to -4. So it's going to be -4 to +4, -4 to +4 in each of the x and y directions. Okay. This we can get rid of. Okay. So what we should see, if I did this right, there are no problems, we should see it just expanding, and I did not do it right. Okay. Get rid of this one. All we need is that time value t. Okay. So attempt to do arithmetic sx and nil value. Okay, yeah, so there's no sx and sy. You have to put them here. Goodness. Okay. Now. So that did not work. Lucky me. 7. Oh, I know why. We did not put our sprite in here. Sget should give us should take a sprite. It does not. I thought sget. Hold on, gotta look up sget. Sget gets the color, the value of a pixel on the sprite sheet. Oh, it's a value within the sprite sheet. Okay, so we need to do some more math. Okay. So in order to find, okay, so we got the sprite number. SPX, SPY. Sprite number. Okay. Let's do SPY first. Sprite. Divided by however many sprites there are. So this goes from 1 to probably 16, 15. That's 0. So 0 to 15. Okay. So we take the sprite number and divide it by 15. X is the sprite number minus the SPY times 16. So if this is 1 divided by 15, this is 4. We want this to be 4. So this should be 0, and if it's 0, that's 0. So it'll just be the sprite number. Okay, and then what we'll do is we'll do SPX plus X, SPY plus Y. That should be right. All right, let's just get this out. And then SX plus. This should. It's interesting. So actually went one over, and it's not supposed to go one over. This is supposed to be one. This is supposed to be multiplied by 8. Right, because that's coordinates times 8. It's going to be 0 still. Okay. And we're still drawing SX. Okay. Okay. Now that we've got the right so it's not X and Y, it's the position is actually going to be SX plus Y plus that. There you go. Okay. So did you see that? You didn't really see that. So kind of exploded pretty quickly in random speeds. Okay. Let's change how this works. So let's not update T. Does not move, does not change. Okay. Now if let's do it, make it so that the up direction or the down direction will update T plus +1. I think I did this backwards. Okay. So here we go. It's exploding. Now, one thing is that they have different speeds. They have random speeds off in the directions. And what's nice about this approach is that we can zoom in, zoom out, right? So we can actually lerp or tween the explosion, right? So we can actually granularly do this. So let's make it more granular. So now, and we can also move in the opposite direction, right? Okay. Now let's say we, if we hold, if we hold this button, then it automatically does it, right? So if we go, so we made it move pretty slowly out in all directions, right? And we can change this value, you know, just give it a different seed and it should appear different. So we can make it massively expand. T times T. Okay. Massively expand. Oh, it's not going to massively expand because T is not set to anything. We could set T to like 0.1. Just go back to this explosion. Okay. And then there you have the effect. The exploding sprite. That's it.